Recording has started.
All right. So what we are going to do is we want to do a reduction operation where we want to see how much of the domain, let's see this shaded area, is covering what percentage of this rectangular domain that we have. So each of these sections, you can assume that there is a pixel there. So what needs to happen is that we need to go and check out every single pixel and see whether they are activated or not. And basically, we have to loop over all of these pixels to count the number of pixels that are activated, and then the number of pixels that are activated divided by the total number of the pixels would give us just a single number output. So from a domain that is a width by height size, you're going to a 1 by 1 size of operation. So one way to do it, a very bad way to do it, is to bring this data to CPU side and do this in a serial way, because in the end, this process is some sort of a serial operation that you have to add all of these numbers together to get a single number out. So one way that comes to mind is to do it serially by just bringing the entire data to CPU, and we know how to do that, and then count whatever we want to count. The drawback for this is that bringing this much data to the CPU side creates a large overhead for communications between the CPU and GPU. So each time you want to do that, you have to bring a large amount of data, and that transfer of data is very time consuming. Another possible way, that is the first approach that we are going to try, is to do this process on the GPU itself. Because the data resides on the GPU, we can calculate a single number using one core of the GPU, and the cores are not too bad. If your CPU is running at around, I don't know, 0.6 gigahertz, probably the core of your GPU is running around 1.6 to 1.8 gigahertz, depending on what sort of GPU you have. So maybe you would say that it is still manageable to do this type of operation. The calculations would be twice as lower on one core of GPU, but you don't have to do any sort of data transfer between the GPU and the CPU. So if you go to the today's codes, we have cheat sheets for you, and number 25 today, and we have single HTML files if you want to work with those. Just for the sake of coloring them, I've also prepared this multiple file version that basically generated that single file version by running a make command. So if you type in make, basically this command will run and it will generate the single HTML file from the files that basically separate the HTML code from the JavaScript code and the fragment shader codes that we are going to use. So if I open this project, again, you will see that this is just our Fizunaguma code that we ended up last week I've added one canvas to it and one additional shader that we are going to program. And if you go to so you can also have a look at the HTML file E01, I think. E01. So the HTML file basically replaces all of those commands and all the file, the content of the files that we had. So nothing is changed. If you look at the apps section of it, the JavaScript section of it, you would see that everything is the same until I have added this reduction part. So basically our reduction result would be a 1-by-1 texture that we are going to generate in the end. And we need to have a solver that uses a shader. We get our entire domain's texture as the input, and we generate this reduction result. Also, I have generated a signal plot that basically looks at the center of that that 1-by-1 texture that has only 1 pixel by 1 pixel, and just plots that one. So whenever we had a signal plot, I also added a reduction signal as well, so that we can update it and the reduction plot. So if you open that file, either you open the JavaScript, the HTML single HTML version, or if you had a PHP server that you could open the multi-file version, you would see something like this, that this plot is going to show us how much activation we are going to have, and the rest of it is exactly where we left off on Wednesday. So what we need to do is we need to go into that the reduction part. So what we have is that, again, we have set up the precision for the float and the integers. We have brought this center of the pixel, but we are not going to use it for this one because you only have 1 pixel. We know what is the center for that. It's 0.5 and 0.5. The important part to remember is that we have access to all the pixels of the input texture that is whatever size it had. I think it is 512 by 512, if I remember correctly. Yes, it's 512 by 512 is coming inside, and what's going out of this texture is just a single number. So the result of this texture size is actually a vector2 type of integers. So IVEC2 that probably we haven't used so far is a vector of 2 integers. What we need to do is basically loop over all the pixels in the I and j directions, and I less than I size x, and I plus plus, we can do a 4. J, it's a 2-nested loop. A equals to 0, j less than I size of y, whatever size we have in the y direction, and j plus plus. And we can read the color. I'm going to use this function. Remember, we were using texture, and this texture was running from 0 to 1. There is another function called texelFetch. texelFetch we can use that gets the texture input, but instead of using that unfamiliar coordinate system of 0 and 1, you can actually use integers to access the texture values. The way that it works is that this corner is 0 and 0 with integers, and this higher corner there is w minus 1 and height minus 1. So it runs from 0 to w minus 1 in the x direction, and from 0 to height -1 in the y direction. So we can easily access the textures, the texture coordinates. So it will be an IVEC2 of I and J's. And there is something called level of detail that you can pass through the textures, but we don't have any of those used, and the default is 0. So we use 0 level of detail. What it will do, this texelFetch will get the color of that pixel with the indices of I and J and return for us. If the U value was greater than, let's say, 0.5, we want to add a 1 to the total number of pixels that were activated. And this, and then as the output color, we can pass all the channels to be just this sum number divided by the total number of pixels that we had, so that we can get whatever was the summation of this. So we are doing a reduction. We are getting from a texture of size, width, and height 512 by 512 into a texture of 1 by 1 size, because the render target was 1 by 1. So the reduction result was this guy. And this is the source code for the JavaScript tag for with the ID reduce. As the input texture, remember F color is coming in here, and the output color is written into the reduction result, which is 1 by 1. Okay, so we are here literally looping over the pixels. Since the result is 1 by 1 pixel, there will be only one core dedicated to do all of these calculations. And let's see this one works. If I introduced any bugs, typing this code, if I reload, there was no bugs. So what will happen is that we need to run this guy to do our calculations. So in our run sequence, first thing that I want to do is I want to try to see what happens if I place these calculations with the time marchings that we are doing. So each march command, you remember, is marching the solution for 2 time steps. We were previously updating the U signal. Now we do a reduction operator and we update the R signal. So let's see how fast will be this simulation. So as a reminder, if I bring the old code for you guys, number 23 ended up here. Pacemaker was active and I was running the simulation. This was the speed that I could easily run. I could even go faster than this. You can see that the time is just flying, right? Now let's see what happens if I'm trying to do this sort of calculation. I do an activation here so that you can see how fast our calculations are. Okay. I see that doing its calculations is just killing itself to do anything. Remember how fast the other simulation was.
It's about the same, right?
It's about the same, yes.
So
this is actually kind of what it looks like over blue jeans.
So it's not really running. You will be looking at still pictures for a while before the next picture appears, because we have introduced basically a serial operation here. One way to remedy this right now is just you might say that, oh, what I want to do is, let me pause this because it's going to kill my computer. It's not doing these calculations. One way to remedy this, you might say that, oh, probably I don't want to do this reduction operator all the time. I can get rid of this, and since this is the bottleneck, I'll take it outside of this time loop, sorry. And then I place it after this several lines of simulation and maybe place it here. That's one solution. Say that don't want to do it that often. And then it becomes bearable, right? But still you can see that even though right now it's outside of that for loop where we are doing 80 time steps of update and we are doing just one reduction operation in serial, it's visibly slower than before. And show it again. This is the way that the simulation was running. With one reduction, the problem is so bad. Okay, so this is because we are not using any sort of utilization of the power of the GPU. We are doing everything in serial. You can try to do it on your own, bringing the data into the CPU and doing the calculations on the CPU, thinking that CPU is way more powerful. Probably it can do better. You will see that the CPU solution would be probably even slower than what we saw here. So what's the solution for this? So instead of doing the reduction that they did right here by just going from the entire domain in one go into one pixel, what we can do is we can break down our reduction operation into multiple steps. In this scenario, 2 steps. Rather than looping over all the things into one number, we can have an intermediate step that we do the summation over maybe a column of the data, and we reduce that column into just a single pixel there. Now in this way, I will have to generate a width by 1 pixel of data. If I had 512 pixels there, then I could easily dedicate 512 cores to do this type of calculation here. And then I can loop over these 512 into a single pixel to do the reduction, the final step of the reduction. The next calculation that we have is basically this. So I just save this one and close it. It's open. The next thing that you will do is we have 2 shaders dedicated to the 2 steps, step 1 and step 2 of this reduction that we talked about. Right now we are going to see how we are going to implement them. So right now the S1 and S2 are just basically copies of the previous one that we did, that we were naively doing everything in just one go over the GPU. What happens is that I've taken the time to create these 2 textures basically. Instead of having the result in one go, I have generated these 2 textures that one of them will have a width of 512 and 1, size of 512 and 1, and the other one is 1 and 1. The first solver reduces the domain from 512 by 512 to 501, and the next solver reduces it from 501 to 1 and 1. So let's do this implementation. Let's look at the S1 shader that we are going to design. So our S1, basically, we are not going to loop in the X direction because the X direction has a width, right? So I remove that part. So the nested loop becomes a little bit more manageable. But I need to have that I coordinate, so integer I. And that integer I would be, if I want to look at the picture that we were having, the CC that we had, the center coordinate of the pixel now plays an important role here. The center coordinates are changing from 0 and 0 in the bottom left to 1 and 1 in the top right corner. So whenever I get the central coordinate of these guys, I can calculate the ith. And remember, this is width. This is, we have CC of x for the xy is 1, and maybe 0.5 for the y, because we are at the center of the pixel. So the i's that I need basically are the floor of CCX times the width that we have, right? So we need the floor of that to be able to do those calculations. So it will be a, and we need to do a type conversion of floor of CC.x times, I have to multiply it by the size of the texture in the x direction. So, and remember, this is an integer, so I have to convert it to floats because I can't multiply integers and floats. So convert it to float, I size of x I get the I coordinate there, and basically from a nested loop I go to just a single loop, and now I have 512 cores dedicated to do these calculations here in this step. And the next step of it, when I go from 512 to 1, I have to remember that now I have to use the result of that guy over there. So here the texture is coming in. We have a certain size. Now in this time I have to loop over the ith direction. I don't have any j's. The sum is already calculated and is inside the color of that results that we are bringing in, and the j coordinate for this guy should be 0. Remember, bottom was the first pixel had 0 and 0 coordinate, and the last pixel was changing. And since we have just 1 by 1 width by 1 data structure, the coordinate in the y direction is running from 0 to 0, basically. And instead of adding a 1 here, I have to add the color that I'm reading in the x direction, maybe. And there's no u anymore, it's just the sum. And I've already done the division part in this section, so I can remove the division part that I have here. I'm doing the final step of reduction here in this part. Now the single core, instead of, so this step will be done by a single core of the GPU. But instead of doing the calculations by the calculations of 512 by 512, it's just doing the calculations of 512 summations. So just going 2 orders of magnitude down in the amount of calculations that it needs to do. So let's have a look at this guy here, where we are doing a parallel reduction. See, I didn't introduce any errors miraculously in this one. So this is a step 1. I'll write a comment here. Step 1 of the reduction. Step 2. And if we go back to the JavaScript part, it hasn't changed much, except for wherever we had reduce, we have reduce to step 1 and reduce to step 2, and we have to make sure that we run both of them when we want to run them. So I have brought it to this section. So reduce S1 and reduce S2 are the 2 steps that we need to do for the reduction part. And now if we do the calculations on this one, you can see that virtually there is no difference between this and this previous one that we had over here, except this one is running twice as fast because we are doing more skips. So it can significantly change everything. I can even, so right now you are seeing that this line is a little bit jagged because the calculations are not done at every single time step. You can even manage to bring it into the time loop and see the amount of change that you can see in this guy here. So even inside the time loop that we are doing all the calculations, this is way better. So you can calculate it maybe around 200 times faster than what we were doing before, by just doing this intermediate step. So you can do the calculations of how much faster this sort of reduction is when we are doing it in 2 steps. The first step is 512 times faster than the previous one, and then you have to do an additional 512 of those calculations in one core, which probably ends up to be like you are doing 513 summations versus 512 by 512. And there is some overhead with launching a shader, which reduces the efficiency a little bit, but I would say this is much better than what we were seeing before, that basically everything was just stationary and nothing was moving. So you can...
Was there a quick question?
Yes.
So is it possible to do matrix manipulations on the GPU?
Matrix manipulation of what order? Like 512 by 512 or?
Yeah, I mean I'm not talking about multiplying matrices, but like reduction of a matrix to a scalar, if there's a function that can support like contractions, so that all the data is just crunched in one step.
So for different colors or doing the calculations that we are crunching down numbers. So this step that you saw here, basically we were crunching down the entire domain into one. And that was the point, that There is no straightforward way of doing it. Either you have to write a for loop or you have to do something like what we implemented here. So if you're interested in calculating ECGs, the problem is something like this, that you have to do an integration over a space that is basically doing a summation over the space for everything. So you have to break it down. But if you're asking about a vector multiplication or a matrix multiplication, you can do dot products of vectors, like you can type dot and vector 1, like A and B. These A and B were to be vectors. You can do dot products. You can do cross products of vectors A and B, and the result will be a matrix. You can do these ones, but these are limited to the data types that exist on the GPU, and those are basically this list that we have here for the solver part.
Right.
So you can see a list of all the data types that we have. You have integer vectors of 1 to 4, and you have matrices of 2 by 2, 2 by 3, 3 by 3, and 3 by 4, and 4 by 4. These are all the types that you have. So you can do matrix operations on these guys only. But if you want to treat your entire domain as a matrix and do matrix operations on that, you have to implement those matrix operations. I don't know if I answered your question.
Yeah, that answers my question.
Okay.
Thanks, Abzar.
You're welcome. Any other questions? I think, Max, was this what you were looking for?
Yeah, this definitely is. I do actually have a question though.
Yes.
In this, I notice you're first reducing along the columns and then doing one row operation. Does the order you access the memory matter for caching on the GPU?
No, it doesn't. It doesn't matter.
Doesn't.
You can try to do another version. What's happening is determined by this size that we defined here. So if you reverse this to, let's say, 1 and height.
Yeah.
And obviously you have to change these guys here, S1 and S2 step that you were doing. You would see that the performance is just identical to that. Okay. It will start to matter if the width and height are not equal to each other. Then I would say probably do the reduction in the parallel step with the larger number size that you have. So if the height, for example, was larger than the width, I would go with the height. Okay. But usually they say that you should keep your textures close to a square, as close to a square as possible.
All right. Yeah, no, that makes sense. That's just not what I'm used to from non-GPU programming.
Yeah, but
well,
yes.
I assume, right? Because the only experience I had with GPU programming before was CUDA, and in that it was like a non-trivial thing, like setting up shared memory between like warps of threads and figuring out how to do that cleverly. So I assume that's still a thing. It's just that WebGL, this framework, has some clever stuff it's doing in the background so that you don't need to think of it? Or is it fundamentally different in some way?
So if you were to use textures on CUDA as well, you would see the similar performance there, because when you're accessing the texture accesses on the GPU, basically it doesn't matter what texture point you are accessing, because the texture in the end is placed in the global memory and you are accessing something in the global memory. So it doesn't matter which points of it you are accessing. Each memory access will have a cost to it. But we don't have that concept of shared memory here on WebGL that much. We have either global memory and then that's it. Global memory, and then the shared memory that you have is just within the shader, and they are not really sharing anything with each other, uh, rather than the texture that resides in the global memory. So those concepts really don't exist here per se, or they are not accessible here. They may exist somewhere down in the hardware layer, but it's not transparent to us.
Okay, thank you.
You're welcome. If you had, however, generated an array of data that you were sending to the GPU, then obviously the array access would be would depend, but on the way that you access it. But usually you are not able to send arrays that are way too big. If the data is too large, you have to send it in the form of textures. So even for example, that cloud of points that I showed that I was using for visualization of the 3D data, I think the number of points that I had were too large, and I had to send the arrays into a number of solvers, the array of points into a number of solvers, so each one of them was just rendering a different set of points, and then the results of all those solvers were overlaid on top of each other. I think there are a total of 16 or 32 solvers that are rendering that scene that you saw, that cloud of points that I was rendering. Right. Any other questions? Stop the recording here.